This is L, okay? This is L, and that is 1. Yes, and here, what was the other? The frequency, okay? The frequency is in the region of 0 and 1 over 4 times tau. Okay, and these are the 1 over 4 times tau. So these are the formulae that we can use or prove. Okay, I've pulled it up here, and also I will clean this one. Actually, this is also interesting, this formula. Where was it? The square root 2. The square root 2 over omega n. For a long time, I thought that it was me who found it first, okay? And it happens very often that and then, quite unexpectedly, a German physicist told me that he saw this formula already in a German paper in 1948, okay? So very, very long time ago, somebody published it in German language in Germany after World War II. And this was written there, that tau should be less than square root 2 times omega n. It was at the time that even the theory of delay differential equations was not correctly developed. They did not understand at that time why that power series is not convergent and things like that. And so this German professor went after it and tried to check what's the origin of this formula and how it is possible that without any previous discussion or something, this formula was just derived once. Then it was published in a mathematics journal, and it was totally forgotten. And because it was in German, nobody else used it, okay? So when in the 1980s I derived again the same formula, I thought that I found it first, and I published it everywhere many times and so on, and also I could do these nice experiments with it, so it sounded good. And then this guy went after it, and it turned out that this German professor actually worked for the rocket problem during World War II, the V2, okay, the rocket with which they tried to bombard London at that time. Actually quite successfully, but already Germany was exhausted and they had no money to produce more. They produced, I don't know, 20 or 30 rockets like this, and the war was already over. And it turned out that already those German engineers who developed the V2, they already calculated this, because actually controlling a rocket is a very similar problem. Also, they realized that the time delay is very important in it, and when you push the rocket ahead, it also starts to become unstable. So in some sense, the problem is similar to the controlling the inverted pendulum. Of course, after World War II, Germany lost the war, so they didn't want to speak anything anymore about rockets. So he thought that he will try to publish it in a way, the same result what he already did for the rockets. He publishes it related to balancing, okay? But at that time nobody was much interested, okay? So it was totally forgotten. But actually, originally first, it was already, as I told you, the theory of delay differential equations started, it was developed first by a Russian in the early 1950s. And that was the time when finally they could establish it more precisely, and all these calculations and proofs were carried out, okay? Yeah. Actually, a very similar thing happened with the shimmy problem, because in 1941, again for the German Air Force, already they investigated the shimmy of the nose gear of the airplanes, because it was a problem for airplanes landing on high speed, and the wheels started vibrating. And that report was also confidential, and after World War II it was Theodor von Karman who found that report in one of these German research institutes, and he thought that it is important, and it was taken to the United States and translated into English. And that was found, and that is a well-known paper, because in 1947 it appeared in English, and then everybody knew about it. But anyway, that's history. It's a somewhat kind of bad history. We spoke about it, that the knowledge of engineers can often be used for wrong purposes, sometimes good. It depends on politicians and our society, that whether it is done well or not. Anyway, so we should just switch it back. I suppose this will come now, or this should. Yep. And let's speak a little bit about the experiments. That the first thing what we can do, it's also a nice game to measure our time delays. Okay, how much is the time delay? And of course you can do it inversely. So you can say that if I can balance something, then I can say how much is the time delay. Also now you can write a code on your computer which measures the time, and you can do a simple experiment when you have something flashing on the screen and you have to push quickly the keyboard, something, and you can check how much time you need between you see the flash and you push the keyboard. Actually, I did it with my students, and it was very funny. So, measuring human time delay, human delays of reflexes. Okay, if you have on a computer screen, you have something and you have a keyboard here, and you have to, so it is your eyes, okay? It goes to the eyes, and then through your brain you just push one of the keys, okay? And the question is that how quickly you can do this. And it's very much disputed. Maybe the measurements are not really correct or not, but some people are able to do it in 0.1 seconds. Some others say that it's, on average it's only 0.2 seconds, okay, through our eyes and our fingertip, okay? So tau is in the range of 0.1 to 0.2, maybe 0.3 seconds, okay? Something like this. Of course, it depends always on your current state of health, how healthy you are, how much you can concentrate, whether you are sleepy, whether you are fresh, okay, whether you can react, whether you concentrate very much to do it very quickly. And of course, you can do the same so with your arm, but you can try to do the same experiment with your leg. It's also very important in case of traffic, okay? Because when you see that somebody slows down in front of you, the red light of the brake lights come out, okay? And then you also have to push the brake. And then you have a visual information and you have to push the brake. Now, to your leg, it's much longer. So actually what you can do, that you can put a keyboard, use an old keyboard, okay? Which you do not mind if you kick it or break it, okay? You can put it to the ground, and then you see the screen and you try to push the keyboard quickly, okay? And you will see that through your leg, it will be in the range of 0.5 to 1 second, actually. So we react very slowly, actually. Very often it happens, you know, that in a traffic, you try to let somebody go, and you even show him that go, okay? And you have the feeling that the guy, why don't you start now, okay? Actually, he saw your sign, he already pushes the gas, okay? But it needs at least 1 second while finally the car starts moving. So actually we should be more patient, because the delay of reflexes will mean that he's unable to jump immediately, okay? It will need some time while they can react. So in this direction, the time delay is larger, clearly. Yeah. Also, there is another way. I don't know whether you play this game, okay? That usually they say that you will not be able to solve this problem. You keep a piece of paper here, okay? And the other guy should go there with the finger, and I will let it fall, and he should catch it, okay? Now, for me, it was easy because I knew when I will land it. But gee, would you come out and shall we try it, okay? Just you will stand here, okay? And watch for the paper and try to catch it. You can put it over down there, okay? And I will let it down and expect it. Oh, he managed to catch it. He just got it. You see, so it was great. Okay, so could you calculate now what was your time delay? Because what is the length of the paper? I don't remember, it's 20, how many centimeters is it? Don't you have a ruler somewhere here? It's because, of course, the size of the paper is important, because 1/2 gt square will be equal to the length of the paper, to the distance. So how much is this? Don't you know, 20 centimeters or how much? Or 30? Nobody has a ruler, okay? That's bad. I mean, we are engineers and we have no ruler with us. I mean, it's...
It should be 297 millimeters.
297, thank you very much. Okay, now we have an engineer with us, you see, who tells us it's 297, so it's about 0.3, okay? So it's about 0.3 meter, and then the time delay, which will be, the time delay here, it will be square root 2s over g. So it will be the square root of 2 times 0.3 over 10, which is 0.06, is it? Am I correct? And the square root of 0.06 is 0.2 something. So the time delay is more than 2 seconds, 0.24 or something like that, okay? 24 seconds, okay? So actually, she was quite good, but he was in this range somewhere, okay? Which is usually said that probably if he practices a little bit and then he could do it even better. But usually if people are not prepared, they are unable to catch it, okay? Because it happens so quickly that that is difficult to catch it. But indeed, so we are in this region. Now it's greatly disputed that if we are in this region, and this is the average value, what humans can do, then how we are able to balance the 0.3 meter long disk, because that's the 0.3 would require 0.1 second time delay. Okay, so it's very, very, very difficult to do it. And with our leg, of course, we can do it only with the, so if I can do it with the 30 centimeter on my fingertip, okay, but I am absolutely impossible to do it on my shoes. However, if I take a long one like this, okay, then with my hand it's very easy, okay. Anybody can do it. It's absolutely. I even can walk with it to different places and so on. So that's very easy. But I can also put it on my toe, okay, and then I can even do it here, okay. So it's with your leg, although the delay is much longer there, with this longer stick, you can still do it. So actually, the funny thing is, sometimes people think that it's the other way around. It is easier to balance the short thing, okay? But if you ask somebody that tried to balance your pencil, it's impossible. Nobody will be able to do that, okay? So there are no human beings who could do this. It always falls down immediately, almost, okay? So the very short things are difficult. The long ones are much easier, okay? So, yeah, here are the results I mentioned. So, actually, if you want to improve and to do it better, then it's also good if we try to increase our mass moment of inertia, okay? Because this will mean that if our mass moment of inertia is larger, then the time period of oscillation will be smaller. It will be also larger, okay? Because we have larger inertia, we'll oscillate slower. And if we oscillate slower, then this time period will be larger and we will have more time to react, okay? So for example, that's one reason why when we walk through something, we like to put out our hands, partly because it's also an actuator, okay, because we can balance ourselves this way, partly because we increase our mass moment of inertia, okay? And then, so it means that if I turn this guy upside down, okay, and he hangs here as a pendulum, okay, and I measure that how much is the time period of oscillation, then I will see that if your hand is this way, you will oscillate faster. If you put hands this way, then you will oscillate slower, okay? So actually it is better to have it this way, because then the time period is larger, and then you will have more time. And isn't it beautiful? You see, these are the two most beautiful irrational numbers, the pi and the square root 2. These cause the most problem for the Greeks, okay, to find the pi and to find the square root 2. And you just have to divide the time period of oscillation by these numbers, and you will get the critical time delay in these cases. Okay, the rope, okay. The rope dancers, they also do the same, okay. So actually, when they have these very long ropes in their hands, and they try to walk along the rope with this, okay, they actually have the feeling that they use it partly as an actuator, because indeed, you have the feeling that you move to the right, okay, I can always try to balance myself with this, okay? And if it is very long, it's quite, and even if you hold it firmly, okay, then clearly your time period of oscillation will be very large and you will have a lot of time to react, okay? So even when you do these very dangerous tasks, then you can concentrate and you can go through. Now, if we watch at this, the La Banditas, okay? She's Salma Hayek, okay? And she also tries it. Would you just switch the light? Anyway, because you cannot see it well. There is one switch, I don't know which one, which just switches at this one. This one should be switched off. Okay, great, thank you. So here you can see her as she tries to do it. And actually, for the first glance, it looks a bit awkward that actually she pushes it even further up, okay? But actually this is good. So if you put it further up, it's better. And if you start lower it down, or even you start, there are some rodents when they are frightened, they just start going down and it gets worse and worse. So because if they put their center of gravity further down, the time period of oscillation will be smaller, and actually they can fall down easier. Okay, so this is how it was done. Okay, and of course it's not a real rope dancing, but they try to rob a bank. Okay, and she has skates and she has to walk on a very narrow line, otherwise they would explode or something. I don't know the exact story. Okay, but this is how it was presented in this movie. And these are the numbers that I already told you in case of the stick balancing, okay? So 0.3 meters. These are the time delays what we measured. And for us, the average was around 100 milliseconds, although they say that generally people has it around 0.2 seconds, 200 milliseconds. So I often say that maybe we have the 0.3 centimeter long rulers. It's a general because we can play with it, okay? We cannot play with the shorter ones, and the longer ones cannot fit into our bag. Yeah, that's another interesting thing, that if, for example, if our time delay is 0.1 second, it would mean that we oscillate between 0 and 2.5 hertz. But when we have to balance our body, our time delay is much larger. It must be somewhere maybe 0.5. If it is 0.5, then 4 times 0.5 is 2, then it's 1/2, only 0 and 1/2 of a hertz, okay? So actually, when we balance ourselves, we actually usually oscillate with a very low frequency, okay? That's exceptional. It's absolutely true in the case we are drunk, okay? And then we have this very low frequency. This guy, for example, tries to stand up, okay? Oh, that's my mobile phone tries to get a message or something. And you could see this oscillation frequency, which is very low. It's about 1 hertz or something like that, as he tries to stand up and tries to walk away. And also in the evening, when you can see these guys, you can measure actually this vibration frequency as they move to the right and to the left. And actually, it's also in the 1 hertz frequency, if you measure with a stopwatch, that how much they oscillate as they go home, okay? Usually you find these very low vibration frequencies. Actually, he almost fell back, okay? So it's a very, very low oscillation, even one oscillation in 2 seconds or something like this. So it's a 1/2 oscillation. Finally, he manages to get that stuff there, okay? So if you do these experiments, also, for example, they try to do it with in case of sportsmen. It's very important, you know, it's an Olympic thing when you have this, mainly Nordic countries, it's very important when you are skiing and then you have to shoot, okay? And then you have to ski, you can go on only if you could shoot the certain things. And usually when you are tired and you have to shoot standing, it's very difficult because you will vibrate, okay? And your muscles are not in good state. And in these cases, of course, when they train these people who have to ride them on the ski and then to shoot, okay, they try to measure how they will vibrate. And this is, for example, a typical vibration like this, and this is a spectrum, and you see this is between 0 and 8 hertz, and usually those who shoot, they oscillate with frequencies around 1 hertz, or even less than 1 hertz. So they have a very, very slow oscillation, okay? And that's how they are trained, and when to shoot, and how to cope with this small vibration, because when they are tired, then they can do that. Actually, if you, it's funny, you know, in Hungary, it's in the villages, it's a shame, of course, when somebody's husband gets drunk in the pub or something, and usually they cannot go home because they are so drunk that then they are just put out through the street. And wives usually go there with a small carriage, and they put the guy into the carriage and they carry him home because they are drunk. In Scotland, they have a very nice solution for this problem. In Scotland, you know, the nights are dark and rainy and cold, so wives don't go for their husbands. So the husband should get home from the pub with different techniques. And each man has a long rope next to the pub, the door of the pub, okay? And all these long poles are left there, okay? And when they want to go home and they are drunk and they just they worry about it that they fall over, then each guy just gets his own rope, his own pole, okay? And they catch it like this, okay? And then they start walking home with this, okay? And actually, they can do it pretty well because they will push the center of gravity further up. So they will have more time to react. So they have the feeling that they actually like catching a pole or something, okay, because they have more time to react, and this way they will manage to get home. And next morning, the wives will take back, when there is already sunshine or rain, the wives will take back the poles to the pub, and the poles are waiting for the husbands, okay? And they don't have to go for the husbands because they will all have their own pole, and with this they can walk home, okay? So it's also funny, sometimes drunk people can ride the bicycle. So you can see some people will fall over, and then they manage to step on a bicycle, and with the bicycle they are able to ride it, but in the meantime they are unable to walk, okay? So any time when you can you can increase your stability in other ways, just making this vibration frequency larger, then you can do these things. So for example, this was a show, it's a popular show in Hungary, called Fabry Show. There's a guy here who was a kind of balancing artist or something, and now he will balance a whole refrigerator, okay? And of course this refrigerator is very heavy. Actually, refrigerators are not so heavy. I don't know whether you try to carry it. It's only a compressor and it is relatively light, but here they want to increase the attraction that two guys try to lift it up. And then he puts it on his mouth and he tries to balance it, okay? And he manages to do it without falling it down. But actually, as a balancing problem, it's not difficult. So it's very easy to balance. It's very difficult to hold because it's heavy, so he's sweating and so on. So you need the strength. But otherwise, the control is simple. So actually, with the long stick, it's very easy to do it. Although I have never tried actually on my. There is not enough space here, so I wanted to put it on into my mouth and to see whether I can do it on my hand. But it's not so difficult. And actually, if you ever try this, I don't know how you call it, but I know in China it's also popular. This rope walking, when you stand on these. Pose, okay, and you catch it with your hand and you start walking with this. I don't know whether you tried it. It looks dangerous, and it is, because if you fall over you will hit yourself badly, okay? But on the other hand, it's very easy. So actually you can just walk like this, and it's not a problem at all. Actually it's even easier to walk this way than walking on the ground. The only problem is that once if you just, then you will have no time to to back, and if you fall over, you will fall from a height, okay, and this will be bad, and you will hit yourself. So it's a bad feeling, but otherwise the control is simple. So it's not difficult to walk on these sticks at all. It's not a big deal, okay? What is a big deal is this one. Can you see this? Now the guy will show a little, it's like a pencil, it's only 10 centimeters long, okay? It's like this. And he puts a coin on the top of that, okay? And now he tells to the showman that he should try to hold this pencil and the coin on his finger. And of course he's unable to do it, it always falls down, okay? And now the guy will put all these things onto his nose, okay? And that's a real trick, okay? You don't need force for this, but that's very hard to do it, okay? Can you see? He could do this. Actually, it's the one what you would, it would be impossible to do it on your finger, okay? And of course he puts there the coin on the, why does he put the coin on the top? Would he be able to do it without the coin on the top? If the coin is up there, then the mass moment of inertia is larger. Yeah. So actually, he increased the time period of oscillation this way, of course, if it were in the other way around. So actually, he put the coin there on the top because this way he gave more time to himself. Also, it's impossible to do it on the finger because you cannot do it with 0.1, 0.2 seconds, but through your neck you can do it, okay? So you can see many artists in circus and so on, they take a dagger, they put into their mouth, and they put it here, okay? And then they can balance very short things, but they do it with their neck, okay? And this way, it's even faster. So if you see something and you have to move your head, then that's even faster. And then you can balance things when you put it into your mouth, and you do it with your neck, okay? And actually, we have a very, oh yeah, it will come later. Please make me remember that it's also an interesting thing how you do it with your neck, okay? Yeah, the balancing organ, okay? So let's see now how the organs work. This is the stability chart, okay? And one thing which is very important to see now in the stability chart, that we need both signals. So we need both the angle and the angular velocity. It is impossible to balance this thing if you know only one of these, okay? Because the region of stability is separated, okay? It's separated from the axis. So if either P is 0 or D is 0, you have no stability. This stability chart is not connected to the axis, like in case of force control or in position control, which were always connected to the 0 lines, okay? It's further away. It's somewhere here, okay? And as you increase the delay, finally the stable region will disappear. So a very important conclusion, both angle and angular velocity signals are needed. Now, if you look at a book in anatomy, how this so-called inner ear looks like, and probably you learned biology and you learned about this so-called semicircular canals, okay? We have 3 half-circle canals in our inner ear behind our hearing organ, okay? And actually it has 2 parts, and in medical sciences one is called macula, and this is, they also write in anatomy books that this is the static receptor, as they say, and these semicircular canals, these are called as dynamic receptors, okay? And actually what we can realize that this organ gives us the signal about the orientation of our head. This gives the angle signal. It's very complicated because we do it also in space. And the way they do it is also very nice. You see, we have only one sensor, and these are pressure sensors. So we have certain neurons. If you push the neuron, it starts crying, wang, 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 wang. Don't push me or something, okay? So they start firing, they say. They start sending us signals that we are pushed, okay? For tension, they don't react at all. But for compression, they start sending signals. So all our sensors everywhere, they are organized in a way that these tiny sensors will react. So these tiny neurons are placed at the bottom of hair, okay, like the cats, okay, they have these long hairs, okay, and when it is touched, this will be bent. At the bottom, it will push a little bit, a neuron, and the neuron will start firing and sending signal to our brain, okay? Now here, there are a lot of hair, tiny ones, okay, very short ones, not like the cat, which is, I don't know, centimeters long. These are a fraction of millimeter, very, very short ones, but there are crystals on the top of the hair, okay? So they are a bit heavy. They are like an inverted pendulum, a small inverted pendulum. Because they are heavy, in the gravitational space, they will be bent, okay? It will be like the grass on the field, okay? When the grass is long, now all the grass is cut here at the university very nicely, but when it is long, okay, the grass will just fall under the weight of the grass, okay? So it is like a grass field, okay? And as we change the inclination of our head, this grass field, all the grass will go in one direction or in the other, or actually if you are in the vertical position, they will, like a flower, they will open up this way or that way, okay? And from this, our brain will get an information what is the inclination of our head, in what angle it is put, okay? So it's amazing how nice this organ. Actually, there's another part of it where everything is in liquid here, okay? On the top of that, so there is liquid, not air. And there are others which are hanging from the ceiling, okay? And actually, so even when we stand on our head, okay, even in that case, we have information about the orientation of our head. So we are very well prepared, even for those cases, we will rarely stand on our head, but even in that case, or if we are underwater or something, we have an impression that what the angle could be approximately. So this gives the angle signal, and this will be used by the proportional gain, okay? Because p times phi must be go there. Measuring velocity, it's even more interesting. The funny thing is that in anatomy books, it's written that this device measures acceleration. But actually, they are wrong. It doesn't measure acceleration, it measures velocity. Because there is liquid in it, okay? There are liquid. Actually, the three semicircles, they are located in three normal planes. So actually they will provide an angular velocity signal in space. So they will know all the components of the angular velocities, okay? And actually there is liquid in it. And when you start rotating your head, of course the head will move away, the liquid has an inertia, and it doesn't want to move, okay? So when you rotate your head, the liquid stays there, and as the liquid moves relative to the skin or the channel, this hair, which is placed in the ampulla, they call it ampulla, that's a part which is a spherical, a bit wider, like a small sphere, ball or something, okay? There is the hair, and as the liquid starts moving relative to skin, this hair is bent, okay? Now this liquid is close to the viscosity of the water. It's a little bit more viscous, but not much, but the channels are narrow. And that's why the Reynolds number is low. Rho Reynolds number, it's a laminar flow. In case of laminar flow, the force will be proportional to the velocity linearly, okay? Like a damper or a dashboard in a car, like a Monroe damper, okay? So it is the same structure, okay? And this will just bend the hair, and if it bends at the bottom, some neurons will be pushed, and they will start firing and sending a signal. And of course, if they rotate faster, it will be bent more, okay? So it's amazing. So our brain knows that we need both signals, and this will be fed to the differential gain, this will be proportional gain, and with the two together, we will get an information. This is the way we can balance ourselves even when our eyes are closed, okay? It's more difficult, actually. So this sensor is not so fine. And also with age, our hearing gets worse and worse. So actually, with age, if you cannot see and you have to close your eyes, it's more and more difficult to balance yourself, okay? Because this is not a fine, it's not as precise, okay? The precision of these sensors are not as good. But still, even for example, blind people, they can also balance themselves, okay, with the help of this. And usually blind people can hear better. So if you cannot see, this organ gets sharper because your brain will have more data or more energy to deal with these things. Okay, there is one other problem on the other hand, okay? You all saw the movie Gravity, okay? And there you could see that how in space, how difficult it is to move for us and so on. One problem is that if we are rotated in the same direction for a long time, and actually we lose our sense of rotation. And first we can think it is bad, but on the other hand, actually it is good. For example, it gives us the possibility that once, if we have a space station which will rotate and will produce a kind of artificial gravity with the help of the centrifugal force, which has been imagined for a long time, just with these tether structures we are unable to do it properly because it's still unstable, the tethered things. But as they rotate, okay, they will give this force. And actually, if we are rotating always in the same direction, we will lose this feeling of the rotation. The reason is because after a time, the liquids, because the friction between the wall and the channel, the liquid starts moving together with us, okay? So after a time, these, if you are rotated for a long time in the same direction, this hair will not be bent anymore, okay? And we just get used to the rotation. And actually it is good, because if we are sit, for example, on a merry-go-round, okay, where we are rotated continuously, you know these machines in these fun parks and so on, Disneyland and so on, you are rotated in the same direction for a long time, and you see the neighbor and so on, then after a time you get used to it, okay? Maybe behind you see that everything is running quickly, but around me everything is okay and I already don't feel the rotation. So after a time this thing is switched off and it starts working in the local system again, okay? So it's fantastic. We are practically prepared for the space trips also in this way. On the other hand, there's a problem if you stop suddenly. If you are rotated for a long time, and then you suddenly stop, okay? Then you stop and the liquid keeps moving, okay? And this will give you this very false impression that you rotate in the other direction, okay? So that's children often play, that they close their eyes and they start rotating like this, okay? They rotate, 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 and then suddenly they stop and then they start becoming like, you see, drunk people and they are moving like this. And this is because when suddenly they stop, this liquid continues rotating and suddenly their control system is messed up. The problem is with the cooperation of the eye and this organ, okay? This organ will send a signal that you are rotating in the other way around, but your eye shows that you are not rotating, okay? And these two things together will make a totally disorganized motion, so it will be something unclear what is really going on, okay? So these are the cases like this, okay? These twins are just rotated by their mother, and they enjoy it very much, okay, because it's very funny. And this little one starts to go after her mother to the kitchen and just couldn't find her way, okay? And it's a totally funny, disorganized motion. And this is because actually in her ear, which is, she's very young, it's very nicely done, okay? It still rotates further, okay? And then it starts, and his eyes show something different from the one they can see in the reality, okay? So, yeah, we still have time to speak about the vision. So that was about the balancing organ, and it's very nice. But vision is also very important. And for example, there are children, it's very sad, there are some children who are born with, somebody wants to find me, but still night in Hungary, I don't know why they try to phone. They born with this, they call it dry ear effect. It's a very sad thing, okay? If there is no liquid in your ear, okay? Partly you cannot hear well, just very badly. And also your balancing organ doesn't send the velocity signal at all, okay? So this, if there is no liquid in it, it's dry, okay? And it's very difficult. I don't know, even nowadays the treatment is very difficult. Not many people are affected by this, but actually one of my colleagues in Newcastle in England, his second daughter actually had a dry ear effect, and he had a hearing aid, so actually he could learn speaking, but when he closed his eyes, he always fell over. So he couldn't balance herself without looking, okay? Also, they complained, for example, that in England, because during the Industrial Revolution in England, they cut all the trees, and they put all lands and grass and sheep everywhere, you know, so there is not many trees. The problem is that if you go for an excursion in England, because if you see that these are beautiful hills, mountains, everything is green, but very little tree, or almost no tree. And when they go for an excursion with the little one, actually he falls over very often because she has no reference for the vertical line, okay? So actually she walks, and if there are no trees, buildings, nothing, she just doesn't know where is the vertical, and her vision doesn't give anything, and her ear doesn't work because it doesn't give the signal about the angle and the angular velocity. So actually she falls over. So, but how is it then that if this organ is damaged, we can still do the same thing with vision, okay? So the visual system also provides the necessary angle and angular velocity signals. It's a problem that we need the vertical direction, okay? So actually, sometimes when we are in some skiers say that if you have to ski in fog, they say it's very dangerous, because actually during the skiing they move fast this way, that way, and if there is fog, they cannot see trees or nothing. After a time, they just fall over because they have no visual reference about the vertical direction. And during a lot of motion, as they shake their head, also this organ is messed up and they don't know exactly where they are, okay? And there is a further problem which is very difficult to understand, namely that our vision is the slowest. We discussed it, that it is very slow. It cannot recognize anybody in 0.1 second. So how we are able to process the information about the vertical direction, about the angle, about the angular velocity, and all these things, okay? You know, in Nature there was a very nice paper about a funny experiment which showed that our brain works in a different way if we think and if we don't think much, okay? So we still have the visual information. You know these masks, also in China use this when they make a negative of your face, okay? And sometimes you put this mask on your face and it will be a full copy of your face, and then you take this mask and you can see into it, okay? And sometimes when you look at the mask for long, this will look like a real one, so your brain will just make it positive, okay? So in this Nature paper, the experiment what neurologists did, that they had this mask, okay, of the face, okay? Here were the eyes, the eyebrow, the nose, the mouth and everything. And actually it was negative, but what they put, that they put here a small fly, okay, magnet, with a magnet, they put there a fly into the place of the nose. And then they covered this and they said to the, no, how is it? Sorry, first there was no fly, okay? Just the negative picture, and they said that now you will see a face and you should touch the nose of the face. They took away the paper and the patient just had to go there, and usually they put their finger to the positive picture because their brain, they thought about it, they processed the picture, and for them it looked, oh, it cannot be a mask, okay, it must be a real face, and they usually put their fingers into the space somewhere, not to the right place, okay? And then they did an experiment, they put a small red fly or something at the nose, and they said to the patient that now you will see suddenly a face, and you have to hit the fly from the nose of from there, okay? And they took it, and you had to do it quickly, and suddenly they did it to the right place. So when they had no time of thinking, and they did not process the picture, they took it to the right place inside the one, because then they concentrated on the fly only, and they did not process the whole thing. So actually it shows that when we see, there are different levels of the visual procession. Sometimes we do it all along, all the visual processing, sometimes we do it quickly. And the most interesting thing is that there are the so-called functional blindness. That's very funny. The functional blindness means that your eye is totally healthy and still you cannot see. You cannot see anything, so you are blind. But when they investigate your eyeball and all the nerves in your eyeball, it turns out that your eyeball is totally healthy, the nerves are working, they are sending the signals, but still your brain doesn't process it. Now in case of these functionally blind people, there is a famous experiment that namely they are just looking and then with, for example, with a fist, they just do like this against their face, okay? And actually they take away their head. And their neck moves very quickly, as we discussed, and they just do like this. While in the meantime, they see they couldn't see anything. So of course they do the test very precisely because you could feel the air motion or some sound or something from which you could feel, but they do the experiments in a way that all these things are excluded. And actually it turns out that the eye is actually connected to your motional system somewhere through your brain without doing the real visual processing. So we have absolutely still no idea, although we know what part of the brain works with this visual processing, still there are many things which we don't know what happens inside deep, okay? And actually our eyes are connected to our motoric system also without thinking, okay? So now let's see how all these things work, okay? This is one theory which I try to publish, and of course, again, you start fighting with medical doctors and others, and very difficult to see whether this theory is good or not. So, as we spoke about it, the eyes, these are the two eyeballs, and this is the brain, and those are the cortical layers, you know. These are the high-level cortical layers here, okay? And this is where the visual processing goes on, and that's very slow, as we said, okay? So now if we just try to imagine how it goes, okay? You heard about these pyramid cells and so on, and they are in our eye, and they are sensitive for the light, and then they start firing, okay, and sending signals. So it's something like this is shown here, and now they try, of course, usually in monkeys, and they try to trace how these neural cells are connected to each other and how they send signals to each other and how in the different layers of the brain they process it further and further. And one thing they found, which is absolutely amazing and interesting, that actually certain neurons, pyramid cells, are sensitive only for certain direction of light. So these small bars are called Gábor elements, okay? These are named after Denis Gábor, who got the Nobel Prize in 1971 for the hologram, okay? And so it means that there are these tiny things, okay, these bars, and actually if I look at this one, different cells will fire than if I look at this one or that one, okay? So these tiny pieces are processed by different cells. And the reason why they started calling it Gábor elements, because it's also a kind of funny it's a kind of funny Fourier spectrum or something, and similar what the hologram does when they do all these things. So, for example, in case of monkeys, they did it that they took a layer of these neurons, and they realized that all the neurons in this yellow region, these yellow ones, they will start firing if they see such kind of tiny bar, okay? The green ones will start spiking when they see a vertical one. The blue ones will be here and there, they will start spiking. The red ones are sensitive for the horizontal ones, okay? And all this is randomly arranged. So when any time, for example, for example, how nowadays they try to explain that how we recognize a circle. This is what our brain gets information, probably. And suddenly we see, oops, there are certain bars which form a circle, so probably there is a circle somewhere there, okay? So this is the way, this was a Nature paper from where I cut this figure, okay? And this is how we recognize certain things, okay? But in the Nature paper they spoke about the circles and faces, how we recognize it, but for us in balancing, the most important thing is to see a straight line. How our brain recognizes where is the vertical direction, whether it's inclined or not, okay? And actually, if we see a line like this, okay, this is parallel to this one, this is yellow, and these groups of cells start firing, okay? And they will send the signal to our brain, okay? And if we then see these ones, then from these we will realize that, okay, this is approximately the inclination of a bar, what we can see, okay? Or the vertical direction is realized by the green spots, okay? And this will mean that actually neighboring for a little bit the blue and a little bit the yellow ones will also fire, but not so much, okay? And the green ones will fire, and those are the red ones which are horizontal, they will fire just randomly a little bit, okay? And this actually goes, when it's very fast, it goes with 80 hertz, okay? So these neurons just ping, 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 they start sending out an electric signal like this, and they send out, and this is the most, and then it goes up for the layers, okay? And then our brain will put it together, and we still don't understand. You know, while in the meantime, we speak about it, looks like a very materialistic explanation how our brain works. But of course, when you get this deeper and deeper, the mystery is even deeper and deeper. We don't understand what we are, what is our soul or thinking and so on. So there is still a very strong philosophical barrier, even as we get closer and closer to these, with these explanations, and it's a mechanistic explanations, okay? So this way we get the information about the position. And this was in 1997, 1999 when it was published in Nature papers, never connected to balancing. They always speaking about just how we see, okay? They just try to. And 5 years later, another paper appeared which actually stated that we can also see the velocity, which is extremely surprising. That was the next question, that how our visual system is able to give information about the velocity. Because we also need this, because the stability chart needs not just the inclination but also the angle. One possibility would be, of course, as I gave it for the home assignment, that you use 2 past positions and you try to calculate the difference of the 2, and from this you try to figure out what the velocity is. But it needs a lot of processing time and thinking. The idea is what they recognize, that actually those cells which measure this direction, they are also sensitive for motion in the other direction. So actually, if this one moves this way, they will also start spiking, and they will give a combined signal. So actually, this way, you will give an information about the angular velocity, because if this bar is moving this way, then definitely your head rotates. And actually, your eye will give immediately a signal about this. Now, it's very much disputed whether this picture are good or not, and actually neuroscientists, they investigated the problem because they wanted to understand how tennis players are able to hit a ball which comes with 200 kilometers per hour, okay? Because actually, at the moment when with your racket you hit the ball, in your brain, the picture of the ball is just only at above the net or something, so several meters away. So how we are able to predict so well, so much ahead, because clearly they also had this problem that the brain is so slow that actually it would be impossible to put the rocket to the right place when it comes with 200 kilometers per hour. And then they realized that actually our visual system sends a signal very quickly, a ready-made velocity signal, okay? Yeah, it was very tricky. Again, they did a very funny experiment with which they tried to prove it. They had a bar. You see, again, those neurophysiologists who are not engineers, they didn't learn much mathematics. The only thing they know that the velocity is distance over time, okay? So they even don't know about acceleration, forces or other things, nothing about Newtonian mechanics. But they did a very funny experiment. They took a bar, okay? And it was, I don't know, 1 meter long or even longer, and this was rotating about a point, okay? And they asked the patient to watch the bar. But what they did, that in the middle part, okay, they lighted it with a continuous line, continuous light, and outside this part was lighted by a stroboscope. okay? And the stroboscope actually, and this was with continuous light. And they asked the patient what they see. And actually what they saw was like this. All the patients reported that actually they see that the middle part of the bar is a little bit always ahead, and this one is behind. So the stroboscopic part, this part which was lighted with continuous light, it always was a little bit ahead, and the rest, which was with the stroboscope, it was somewhat behind. So they also tried to support this theory, saying that in this way, it means that if you get the stroboscope, our eyes' velocity measurement is messed up because it gets only at certain moments, and the cells cannot work well. And they will be delayed in this way. But where it can measure the velocity, our brain is already projected a little bit ahead, because from the velocity, we already can project that. And this is the way, for example, that finally we hit the tennis ball, because our brain already projects the ball ahead where we have to hit it, and not where it really is at that moment. So it's really crazy. And actually, there are also other theories about it, how the... That's also funny. Again, neurologists, when they speak about it, they say that finally this velocity measurement is working like a finite difference method, because they say that in the layers of vision, there are so-called exhibitory layers and inhibitory layers. In the inhibitor layer, a neuron, because the neurons are all connected, okay? They are connected this way, actually in thousands of ways, so we still cannot see it clearly because it's so complicated. But there are certain neurons which will start fire if they get another neuron to fire, so they just transmit the firing. But there are certain neurons which just behave in the opposite way. If they get a signal firing, they don't fire, and if they don't get anything, they will start firing. So actually they do the subtraction, they do just the opposite, okay? And in this way, for example, when visual information arrives, they can propagate, for example, through this way, but it cannot propagate that way, because that one will not further. And this way, like a finite difference method, this is how it could work, okay? Then this theory was challenged, and there are many, but you see, this is now where we are. So at least far as I know, and if you read these papers in neuroscience, and very interesting, usually it's a different language, hard to understand, but the mathematics is usually very primitive. It's just secondary school mathematics what they use, and natural logic, okay? But it's wonderful. Anyway, so let's go back to the problem. We have the eye. If the visual transformation is fully processed and sent out, it takes 0.6 seconds, and clearly we wouldn't be able to balance the stick. But actually when we start learning it, so the first time when you try to do this and you put it on your, actually you do that, because at the first time when you try it, it always falls down. So actually you see that, okay, it falls, I should push it, but it's already too late, okay? And then it needs a time while you get used to it. You learn what kind of P&D you should use and how to tune yourself, okay? It's a learning process, so actually you start programming your neural network, which is inside, as down they interpret in many places. But when you already learned, okay, there is this ancient part of the brain which is called colliculus superior, and it's a very primitive part of the brain. Actually, on many animals it already exists. Actually, I think the reptiles, I think the crocodile and snakes and so on, they already have this kind of brain, and they can move very quickly. Okay, their motion control is already very good, although their brain is not much developed. Okay, and this old part. Now, in the case of human beings, monkeys, and so on, we just cannot study it at the moment because it's so much deep in the brain. Okay, so we cannot send in any sensor. But actually, this is the one which is also connected to the eye. Okay, and this is the so-called mediotemporal loop, a short loop where actually, without processing the signal, our eye is connected to our arm and our visual system, okay? And actually, in this way, we can reach already 0.1 second. So actually, when we already learned how to do the balancing, then probably, that's my theory, but again, it's not absolutely not sure it's true, probably we learned it here because we had to think. But when we learned how to do it, we send the command down here to this primitive level, okay? And it's like programming on a low-level program. We just force these neurons to work and do the job, okay? And then we do it without thinking in some sense very, very quickly, okay? Okay, and just before the break, that's the best thing. You know, there are two things. There is one thing only a father can do, even not the mother can do with the kid. And this is what Julius said in England, they said it is to throw the kid into the air, okay? No grandparents, no relatives, no mother, nobody, just the father. So it's the father's responsibility to throw the kid in the air and to catch it, okay? Kids enjoy it very much, they will laugh and everything, but they need this trust, okay? And you need the force, because you need force, and you need the precise controlling, and it's dangerous a little bit, so you don't want to hit your kid. But that's one thing what only fathers can do, so it's the right of the fathers to throw the kid. There's another one I saw recently, and this is the second one, okay? This little kid still cannot walk, okay? But he can already stand. So it's a double balancing problem. It's the stick balancing and the self-balancing together, okay? And it's interesting to watch the little kid. Sometimes he looks to the camera, okay? And sometimes he turns back and looks at his father, okay? It's interesting to see how he tries to find the reference point, okay? And in spite of the fact that he's still, okay, now he looks at his father, okay? And then again he looks at the camera, which is probably much safer as a vertical direction. And so they can do it together. So it was nicely done, and he deserves a kiss from the father, I suppose, at the end. Yeah, okay, you got it. Okay, so now we will have the break, okay? And then we will speak still a little bit about the digital balancing, how it goes, okay?